Okay, we're back with part 2 now on our designing a vacuum tube amplifier. And where we left off yesterday or on part 1, was we did the power supply. We talked about that a little bit. And today where we're going to start is deciding on the preamp and driver section. Now that can be really complicated, and there are a lot of different choices for that, especially when you're dealing with a push-pull amplifier like we are. In order for a push-pull amplifier to work, you have to have an out-of-phase signal. In other words, the reason it's called push-pull is you have two tubes on your output connected to your output transformer, and when they're both kind of sitting at the middle of their conduction zone, okay, where they can, they're biased about halfway turned on, and when one tube is going positive, the other one is going negative. When the other one's going positive, the other one's going negative, and they push and pull back and forth. And in order to do that, what you start out with is one signal. But the idea is you have to have two signals in opposite phase, 180 degrees out of phase from one another, in order to drive both of the output tubes in their respective direction. So in order to do that, you have to be able to split that signal and turn it into two signals that are 180 degrees out of phase from one another. So in order to do that, you have to kind of decide how what design of circuit you want to use for that. And I've printed out a few things here, and there's a lot of information out there. But when we look at a few of these things, okay, the simplest way to do it, okay, is, let me just take a piece of paper here for a second. Simplest way to do it is you have your input signal, okay, and coming in you have your two tubes for your push-pull, right? And I'm just going to draw triodes to keep it simple. And you have something going like this. Alright, and then this comes out, and I'm leaving circuitry out. Okay, but I'm just doing a simplified drawing. Okay, and you have something like this. And of course, when this one is going in the upswing, this one needs to be going on the downswing. Okay, at the input, here and here. Okay. And the early way they used to do it was they would just put one tube in there that would just act as a phase inverter. So, of course, we have capacitors and things in here. I'm going to leave that all out for now. But basically what you would do is your top half would go in phase, right, like that. Your bottom half, you would take another little tube, okay, and you would set it up, just do a plus there, and you would have your cathode go down. I'm just really oversimplifying this. And you would come out of here, your capacitor, and you would go in here, and this is a cathode follower, okay? So and this would tie in up here, okay? Again, I'm leaving out a lot of components, but the idea is, by putting this cathode follower in here, anything that comes out of the cathode is going to be inverted with respect to the grid, to the input. So essentially all this is used for, and of course you're setting this so that the gain, no gain, okay, or unity. Okay, so what you're doing is this is going to invert the signal and put it into your 180 degree out of phase push-pull tube. And in that way they would work. Now there are a lot of pros and cons, and we can talk about phase inverters and preamps and drivers, but I'm going to skip way ahead. I think that's way too much for this conversation and for this series. But we'll just say that's one way of doing it. One of the other ways, I'm just going to mention two or three. One of the other ways that's common is called the long-tailed pair. Let me see if I can find an example of that. I thought I had one here. I don't have one. Anyway, well, here I have some actual schematics of amplifiers. Let's look at these. So here's an example of a long-tailed pair. Okay, so what's happening is you're coming in, so here's your input. You're coming in, you have a dual triode tube. That's all this is. You have two tubes in one. Okay, and the first one pretty much is going in, coming off the anode, and it's feeding into the first tube. Similar to the simplified design, with the single phase inverter that we had. The second tube, if you look here, is feeding off of the output of the first one. Okay? And in essence, it's actually going to be out of phase from this one. And what's going to happen to that is it's going to go down into here and feed this one. Okay? So this type of phase inverter you see in a lot of the guitar amplifiers and so forth out there. Now there's people will have debates over these on forums and things, and there's lots of pros and cons to everything. I'm just showing you what's out there, and then I'll show you what I went with on my design. Okay. This was a very popular British amplifier back in the day, called the Quad 2. It was made by a company called Quad. And as you can see how it works, it's a really, it uses two pentode tubes. Okay, so you have really high gain, and basically your preamp and your phase splitting and your drivers are all two tubes. Okay, so you have basically from the input to the output tube, you got one tube in between there. So this guy and this guy are acting as your phase inverters. And I showed the current paths here. They act as your phase inverters, they act as your preamplifiers, and they act as your drivers all in one. Okay, so these amps had pretty decent output. I think they were rated maybe 15 or 20 watts of output power, and they're deriving it with only one stage of preamp slash driver slash phase inversion. Okay, so that's what's unique about them. The problem is you're working with pentodes, and a pentode tube is just, they're really susceptible to noise and hum. They're very high gain. I mean, even you get your hand around the tube and it'll hum. So you got to kind of watch that, and through careful mechanical design and electrical design, you can make this work, and it's an excellent design. But you have to remember that deal with pentodes, you're dealing with all your gain in one place. It's kind of putting all your eggs in one basket. This is a very popular amp, a company called Dynaco, and these were sold as kits and as pre-built amps. And the more popular amp that they had was the ST70, which was the bigger version of this, and it used a different topology than this. But if you look at this guy, this is more similar to what I went with. And what we have here is we have a just a normal preamp tube. So all we're doing, your gain is right here. This is where you're picking up your gain. Okay. And then you have what here is your phase inverter, and this particular type of circuit is called a cathodyne. Cathodyne. So it's a cathodiene phase inverter. And this phase inverter has little or no gain whatsoever. Its whole purpose in life is to split the phase so you have two outputs. So if you look, these guys are set up in such a way that the output at the anode and the output at the cathode is very similar. Okay, or it should be identical. It's supposed to be balanced. So this thing's sitting right at the middle of its bias point. So as as it swings up, this guy can drop and this guy can raise, and the opposite happens when it swings the other direction. This guy can drop, this guy can raise, and that's your phase inversion right there. These two things work together. Now, where did that come from? And I'll show you where 2 amps that I got most of my ideas from, what I chose to go with. A while back, a gentleman in England by the name of Williamson came up with a very ingenious design for an amplifier. And he was one of the first ones attributed with using what's called global negative feedback. And we'll talk about that later. That's one of our things we're looking at next. But the thing I really want you to look at here is the design. Okay, now if we take this out of the picture, take these tubes out, you basically have a similar situation to what's going on with the ST35. You have a triode preamp. So that's giving you your gain. Okay, then you're going into this cathodiene phase inverter. Okay, so you're splitting the phase between the anode and the cathode. You're raising this up. Okay, so if you look at R5, that's a 22K resistor there, so you're bringing the cathode way up. Okay, and you're driving, in this case, you're driving a set of drivers. And what these guys do is they provide some buffering between this and this, but they also add another stage of gain. This amplifier was designed to drive a set of KT66 tubes, which are a higher output than they're about double the power of the 6BQ5s. And they also have higher drive requirements, much more than this little cathodiene circuit can actually put out. So what they do here is you come out of your cathodiene, you go into a set of drivers, which boosts your drive voltage. So you have a higher voltage swing here. Then you run that into your outputs. Okay. Now, this amplifier got a lot of attention in its day because, number one, of the sound quality and the amount of power it got for the sound quality. But the biggest thing, though, you have to look at is there was a negative, and that is with all these stages comes instability. If you didn't carefully choose if you just willy-nilly put one of these together, you could very easily get this thing to oscillate. It would oscillate, it would motorboat, it would be unstable. You'd get ultra-high frequency oscillation, which would cause the tubes to red plate and things, and they would be operating at an inaudible frequency, so you wouldn't even know what's going on. The amp's oscillating, it's getting hot, you don't know why. It's playing fine, it sounds fine, but it's getting hot. The reason the tubes are getting hot, they're oscillating. So, all these stages, you could have a problem. The plus side, you're amplifying the signal slowly over multiple stages, so no individual stage has such high gain that it's going to pick up a lot of noise, background noise. So, again, the amp could be pretty quiet if it's designed right. It could oscillate, but it was a very versatile circuit. Now, since I'm using a 6BQ5, in my opinion, one of the reasons I went with this type of design is the cathodiene, the output of it is just perfect to drive a 6BQ5, which is a very efficient, sensitive tube. These guys don't need a whole lot of drive voltage to drive them into their maximum output. So I can basically have 2 tubes, okay, which this is a dual triode, so this would be 1 tube here with 2 elements, two tubes in it. And these 2 here. So I could basically have this, and this 3 tubes, and I have my whole amplifier. What's so good about that? I'm using triodes, so nothing has ultra high gain. so low noise. I have simplicity, so I'm not going to get oscillation as easily because there's less components to cause the oscillation. Cathodines are very well balanced if you design them right. So you have a very symmetrical drive signal into your output tubes. And since I have the proper output voltage for the input of the tubes I'm using, I only need to come straight out of here into here. So for what we're doing, to me this is the most practical approach. Now, if you're making a stereo, you're building two of these, you can get a little bit creative. Let's say that you needed a more gain than you had, okay, than we have right now. For whatever reason, you're going to use a low input signal or something. I could substitute this one with like a 12AX7, okay, and keep this one as an ECC88 or 12AU7. So I would have two of these tubes. They'd be different styles, and I'd use half of one and half of the other for each channel. So I'd get my higher gain with my 12AX7, and then I'd get my phase splitter and my stability with my ECC88 or 12AU7. You're going to find out there's only a few tubes that really fit the bill for this particular application. High gain tubes don't work well with this. You want a lower gain tube with lower noise, and really the 6SN7 and the ECC88 turn out to be the two best tubes for that application. So the other thing about this amp that was unique was the fact that it uses global negative feedback. Okay, and so you can see we're tapping right off of the output transformer, right where the speaker goes, going through a resistor. This is a very simplified design of it, feeding it all the way back to the first preamp stage into the cathode. And basically we're kind of back feeding our biasing of this first tube. So what's that going to do? That's going to reduce the output of the whole amp. So you're going to lose a little bit of volume. Okay, you're going to lose volume, and you can lose anywhere from 10 to 30 dB of gain through the circuit. So you're going to lose volume. However, it's going to flatten out the response. It's going to make the bass a lot more prominent and a lot smoother sounding. This, almost every amp now, modern tube amplifiers, uses some form of global negative feedback like this. Now, of course, it has to be negative. You take this and put it on this tap here instead of this tap here, you're going to turn this into a giant oscillator, and you're going to make a big loud noise, and it's very unpleasant if you ever do it. But if it's in the correct phase, once again, this signal is out of phase with respect to this at any given time. So basically this is going to cancel out what's coming in here to a certain degree, controlled by this resistor. Now, determining all that can get pretty complicated because your bias voltage is set normally by your cathode resistor. But now you have current flowing through this loop as well, through the coil to ground. So essentially what's happening is you have two different current loops for this, and this one's moving with respect to the signal. So calculating that can be a lot of work. Now, that comes to what we're going to see at the end of this. All right, we'll come to that here in a little bit. Now, last amp I want you to look at. This is from a book written by a gentleman by the name of Morgan Jones, and he has a book entitled Valve Amplifiers, and this is out of one of his older revisions of that book. And this is an amplifier that he designed from the ground up using mathematics and then using experimentation, kind of like a recipe. And he came up with this little concoction, and it turned out to be a pretty perfect design. You're going to see a lot of similarities in this with my amplifier that I'm going to show you here in a little bit, because really he did a fantastic job of designing all this. I made a few changes, but not much. Okay, and as you can see, he drew it a little different, but this again is a cathodine. Okay, so you basically have your first stage here for your gain. It comes directly out of there, and it's direct coupled through this little 330 ohm resistor into the input of your phase splitter or of your cathodione. Okay, and these are equally split. You have your positive going output, your negative going output here, or your non-inverting and inverting output, we should call it. Okay, and the output section is cathode biased. Okay, so it's kind of a little bit of self-correcting. Okay, if you notice, he fitted a couple of little 68 picofarad capacitors, shunting your grid leaks here, and the reason that those are in there is he was trying to clamp off the high frequency bandwidth component of this amp. In other words, the frequency response of this circuit is very high, up into the well into the megahertz, and of course we don't want all that. That makes it entirely too much possible for this amp to oscillate at very high frequencies. So we're just going to clamp some of that off with that. That's why he did that. I don't see that very often in amp designs. I think that's kind of a neat addition. So I included that in mine. The other thing is the regulator. One of the biggest drawbacks with a cathodione-based system is this voltage in here is extremely critical because you're direct coupled, if you notice. This is not capacitive coupled. And because of that, any change in your voltage up here could totally upset the apple cart here. It can also affect here. So all the stability that this amp has and all the symmetry that it has can go to pot if you don't have a clean voltage. So you really need a regulated high voltage power supply, which is kind of a challenge. And he never goes to that in his book as to how he derives that. So I'll show you with what I came up with that I'm going to try, and hopefully it'll work for us. The other thing you don't often see is usually your B plus will come straight out of your tube right here off the main filter. And they'll use the highest amount of voltage to drive that. If you notice, we're driving after the choke, the filter choke. So we have a choke filtered power supply feeding this. Now that's not always really necessary because these amps, because of the way a push-pull output section is designed, they tend to cancel the hum out. Okay, and again, we could get into a lot more than I care to right now how that happens, but it won't hum pretty much. This section here, if you drive it on here, this is enough filtration that the output section won't hum. But he wanted it to be ultra filtered. He wanted the quietest, dead silent amplifier you could get. And the only way to do it is with that. But the drawback is to have a choke that can produce the level of current that you really need to drive 2 channels full power. This is going to be a very big choke. And you're going to see the choke that I'm going to use, a 10 Henry, is going to be every bit as big. It's going to be almost as big as the power transformer itself. It's going to be very large. And it's just, again, you can't take place of iron. You got to have the iron. All of these have to have enough iron and have enough magnetic properties to conduct the power that it needs to do, or to conduct. Okay? So, you're going to see here in a little bit why I chose that design. Alright, now, will you need a driver after the phase inverter? Again, we talked about that. With the Williamson amp, as you can see, you needed it. You needed that because that extra power is required to drive the bigger output tubes. On the smaller 6BQ5s, we don't need a driver, but you need to think about that in your design. And last of all, feedback. Now, if it's an audio amplifier for music, you want feedback. That's what's going to give you the good sound. Some guitar amplifiers do not use that. They want the high volume, they want the breakup, they want it to distort, they want that high edge, crisp sound, and no feedback is going to give you that. Okay, so again, that's a matter of choice. All right, I'm back. So next page. So the next thing you want to decide is if you're going to have volume, tone, input selection, etc. Now, that's really important. There's a couple of trains of thought for this. Number one, all of those amplifiers I showed you, all these things here, every one of them will pretty much work if you plug your MP3 player directly into it. Now, what's the most common use for a little amp these days, People don't use cassettes and records and things as much, except people who are really into audio and so forth. But you may just want something to amplify your computer, to come out of the output of your sound card, or your cell phone, come right out of the output of that. They make a lot of really nice little cables you can get like this that have the 1/8 inch jack to RCAs, and you plug that into your phone or your MP3 player, and you can go straight into these amps, and it works perfect. You don't need anything, okay? Now, you may want to have channel switching. Let's say you do have a computer, an MP3 player, a cassette player, and a CD player. They're all similar line levels. Those are all called line level components. You may want to put switching in there for your inputs. You may want to put multiple inputs. And you may want to have the ability to attenuate the volume, to turn it up and down. Okay, that's always a good option. And you may even want to put a tone section in there. Maybe as simple as just a tone control, or maybe you may want to do a bass and treble control, bass mid-range and treble. You get crazy with it if you want. Or you may do what I'm going to try, which is something I've never tried before. This is a new thing for me. I'm going to experiment with it, and I'm going to have fun and see if it works. If it doesn't work, I'm just going to not use it. I'll disconnect it. But we'll talk about that in a little bit. But you do need to decide on that. If you're going to have those, you're going to, need the extra power in your power supply to drive the extra tubes. So you need more filament current from your filament windings of your transformer. You need a more elaborate power supply. Now you're talking about, you need a quieter, more regulated power supply for your volume and tone control, because again, and then if you try to go with a Phono Stage, you have to put a Phono preamp. Those are ultra noise sensitive and ultra critical, okay? We're not even going to get into designing a Phono Stage in this series at all. But suffice it to say that if you decide to do that, you need extra real estate on your cabinet, or you need 2 separate chassis even to go to. You need to have the room to mount everything. You need the power supply to handle it, and then you need all the design of the circuitry for all that. Okay, so that's a big choice if you decide to do that. Volume pot's not a big deal. You're just adding one pot, either a 1 meg or 500K or 100K, depending on the input, and tying one end to ground and the other end to your input, and the wiper goes to the end. So you would just put it right here, and it would just kind of parallel across this and go right in. Very simple. You could couple it through a capacitor. There's all kind of ways to do it, but it's just simple. It's just adding a pot. All right, step 7. Once you get all those decisions made, it's time to sit down and start drawing out your schematic. You have to really decide what you want, okay? And the only way to do it is to get pencil and paper, or if you're really good with CAD, if you have the software like Eagle CAD or one of those programs, you can sit down, and it's like drawing a recipe, make a plan, okay? And a schematic is just like having a recipe when you're cooking, okay? And something that's really important to understand, even though you have a recipe, your amp may not turn out the way that another person's did with the same schematic, okay? Just like if you bake a cake, you can open a recipe book And you can give that same recipe to someone else. You can both use the exact same recipe to bake the same cake, and your cake will be different than that other person's cake. Why? The ingredients they use may be a little different. The altitude that you're cooking at may be a little bit different. The oven that you're using may be a little bit different. The water you're using might be a little bit different. All those little differences add up to one big difference. And you can, all of a sudden, from the same recipe, have two different cakes. Schematics are the same way. Don't be frustrated if you sit down and you decide to mathematically calculate all this. Let's say you want to design the gain stage for each one of these. So you want to know how to bias this. You want to know what your anode resistor is, what your cathode resistors are, what your gain is. You're going to take the mu of the tube, and you're going to multiply it to figure out the gain. All that stuff, you'll sit and do that, and then you'll build it, and it won't work exactly the way that you calculated. That's because it's the real world. That happens. That's normal. The only way to get consistency like that is to build a prototype, like what we're going to do, work all the kinks out of it, and then have a controlled environment in which you build these amps and then mass produce them in that controlled environment. Now, a manufacturer, that's what they do. That's why they can make 1,000 of that amp and all 1,000 will be the same. Okay? You're making a one-off. It's never going to be like a factory builds it. Okay? It's going to be a prototype. It's going to be custom. It's going to be a one-of-a-kind. It can be as good or better than the mass-produced ones. However, it will be unique. And you will have to do little tweaks on it. You're not going to just build it and the very first time you turn it on, it's perfect. Okay? Even if it works the very first time you turn it on, you'll probably find that there'll be little tweaks you can make to it to improve it. Okay? That's part of the hobby. That's, to me, what makes it appealing to me. I really don't care if this is perfect the first time I turn it on. I actually almost hope it's not, so that I can extend it and have some time to work with it. It's a hobby. This is a hobby. I don't need this amplifier. I can go to the store and buy one all day long. This is really about the hobby. And as long as you take that attitude as well, you're going to find out that you're going to enjoy this. Okay? Don't try to make it into something that it's not. Okay. Once you get your schematic drawn out, which we're going to end with the schematic on part 2 here, the last part is to determine the physical layout. So a couple of notes you may want to remember. Make sure that your output transformers, your power transformers, and your chokes are magnetically out of phase to reduce crosstalk. So what do I mean by that? Let me grab a couple of transformers and I'll show you. So let's pretend this is your power transformer, even though it's not a power transformer. And let's pretend this is an output transformer, even though it's not an output transformer. Okay? If you put your transformers like this, or like this, then the lines of magnetism are in line with one another. Theoretically, electromagnetically, these can have interference. They can interfere with one another. The hum from the 60 cycle hum from the transformer can induce itself onto your output transformer. And the sound of your output transformer could induce itself onto the power transformer and come through your power supply. Okay, theoretically. So typically what you're going to want to see is if you have two transformers next to one another, you want to turn the lines of magnetic flux, okay, 90 degrees to one another. So all of your transformers, so if you had a stereo, you would have your power transformer here. You would have your one output transformer turned 90 degrees to this, in this direction. And you would have your other one 90 degrees this direction. This guy will shield the two outputs from one another. And since they're magnetically out of phase from one another, these two are not going to crosstalk and these two are not going to crosstalk. Very important that you do that. Okay? Good physical design is every bit as important as electronic design. You can have the most perfectly designed electronic amplifier on earth, and if you do a bad job of your layout, the amp will fail. It will not be good. It won't work up to your expectations. All right? So very, 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 very important. Okay? Locate your inputs and your controls away from sources of noise. You certainly don't want to put your RCA input, for the amp, right underneath your power transformer. That power transformer is just a big noise generator. And what's going to happen? The most sensitive part of the amplifier is your preamp at the beginning. Okay? It's sensitive because it's supposed to take the smallest signal and amplify it. That's its job. So if there's noise, it's going to amplify that noise. So always make sure that your inputs are well shielded and keep them away from your transformers or from keep them as close to ground and shield as possible. Okay? That'll reduce or negate the noise. Okay? Allow proper spacing for your rectifier and output tubes. I see this mistake made a lot on home built amps. Going back to our transformer, if you have your transformer here, and let's just pretend this is your big power, your rectifier tube. Let's just pretend for a minute. Here's your power transformer, here's your outputs, and somebody will put the rectifier right like that. These will get very, very, very hot. And this is metal. This is going to radiate heat right into this bell. This bell is going to just keep heating up. The transformer's already getting hot from normal operation, from the coils inside. This is adding to that heat. Now, what's inside of a transformer? Okay? I'll try to show you here what's inside of a transformer, if I can find it. Alright, I'm not finding what I want. Basically, I'm sorry I don't have the right stuff here. Basically what you have is some very thin wire like this. The only difference, this is bare wire. They take this wire and they dip it in enamel, okay? Kind of like varnish, like what you'd varnish your table with. And that enameled wire, that enamel is very thin. It's just a layer of like nail polish. And that's wrapped all the way around in there, and those wires are touching one another. And the only thing preventing those turns from shorting against one another is that tiny thin amount of enamel. Okay, I have all my enamel wire put away right now, so I thought I had a little roll of it out somewhere, but I don't. But that wire will short, and having this tube right here will actually break that enamel down inside there. That enamel will then kind of wash away. It'll melt. And then you have this. You have bare wire touching bare wire, and your transformer will short out. So make sure, they say to have one, so if you look at the width of this tube, one tube width away from your transformers and from all your other things. So really, about there would be good. Not there. There. Okay? Same thing with your outputs. This is an output tube. And as you can see, they get really, really hot. Especially these high-powered ones. You got to understand, when these things are biased for Class AB or Class A push-pull, they're already conducting half of their rated power, or close to 20% or whatever of their rated power in standby. So just sitting there, they're going to get very, very hot. Okay? So Again, if they're sitting right in, if you have your output transformer sandwiched right in between them like that, you're going to fry your output transformer. You're going to shorten the life of that, and the tubes don't have any airflow or enough air around them to radiate the heat. They have to radiate their heat. They need to be hot to function, but if they get too hot, you shorten the life of the tube and it will fail. So spacing between your power and rectifier tubes is critical. Okay, make sure you do that. Use a big enough chassis. Okay, don't try to get something like the sheet of this paper and put a stereo 50-watt amplifier on it. You're not going to do it. You can cram everything on there, but you're going to be sorry. Everything's going to be too close. You're going to have noise. You're going to have overheating. The transformers are going to run too hot. They're going to crosstalk magnetically. No good. Okay? All right. If you're using your point-to-point wiring, this is an important one. Lay out your terminal strips and your tube sockets very carefully. And what I mean by that, okay, so here's different terminal strips. Now when you're doing point-to-point wiring and you're not using like the phenolic tag board with the little tags on it or the little solder pots in there, you're going to use these. And if used properly, they can make a really neat looking amp inside. But you can't hodgepodge these in there. You got to kind of sit down, look at your schematic, look at where the components are going to be in proximity to the tube sockets, and then strategically place these out. To the point where if you need to take a piece of paper, even if you have to tape paper together to be the size of your actual chassis, and then just full sized, full scale, put these down and trace them out on the paper and trace your components out. Yes, that's a lot of work, but in the long run, it's going to keep your amp from looking really messy inside, because what happens is you always think you have more room than you have. Anytime you start soldering all these parts, this doesn't look like a whole lot, any of these. It doesn't look like well, here's four resistors. How much room can that take up on my tube socket? But then you realize your tube socket's only that big. And all of this is going to be on that. And then you have all these things connecting to it, and all these wires. Before you know it, that tube socket is crowded. And you didn't plan to offload some of those things onto terminal strips. Okay? So sit down, lay it out, draw it, and figure out what you're doing. There's going to be big empty space underneath your chassis where your transformers are. And you can't really drill through there because you'll drill into your transformer on the other side. Okay? If you are going to have something underneath where the transformer is, you have to put that strip ahead of time before you mount your transformer and pop rivet it in there, and then mount your transformer on the other side like this. If you don't, you're going to have a hard time. You're going to have to take the transformer back off. Everything has to be planned. Okay? Especially when you're dealing with a stereo amp, because now you're doubling. Everything's going to be double. This is 1 amp. You forget this is only half of a stereo. You have to do this another whole time for stereo, plus your power supply, which you don't see here. So very important. Okay, so lay out your amp carefully. Okay. Same thing with the eyelet board. If you're using a tag board, kind of like on the Macintosh, the old Macintosh MC30s, MC40s, and so forth. Again, how are you laying out those components? How are you laying the wires out to the tube sockets? You got to do that up front. Guitar amps use that a lot. Very important. Okay. And last on this list, and then we'll look at my schematic. While it's possible to design each section using tube charts and calculating the values for each component, and you may want to choose this exercise for the experience, it may also be desirable to look at the designs that already exist and to work from them. you guys got to remember there's nothing new under the sun. You know, if there's something you're thinking about, somebody most likely has already done it, at least to some degree. And why reinvent the wheel, you know? So in many cases, you'll find out that you don't need to reinvent the wheel. Many times there are things in a one-off design that you can't calculate, and even if you use an existing design, don't be surprised if you have to tweak it a bit to get it to work with your components. Remember, the stuff you're going to work with is a lot of times modern components. They're a little bit different than the older ones. So you're going to find that you're going to have to adapt your design, you know, and your build to what you have. Okay? So with that being said, I'm going to show you where I'm at. I think I got the whole thing in the shot here. So as you can see, there's a lot of similarities to that Dynaco and to that Morgan-Jones amplifier. All right. I did go with the cathodiene. I drew mine a little different. And I did go with, you know, so we have our gain stage. I went with a 6DJ8 or E88CC. Those are all the same. 6922. Those are all the same tube. Okay. Just different manufacturers. And I'm keeping it simple. All right. Now, the calculations that Morgan-Jones used really split hairs, and I like it. And he found how to use some standard component values to combine them, like for this cathode resistor and for this feedback resistor, to get an exact resistance that's perfect for this. A lot of times designers of mass-produced amps are going to use mass-produced parts. They'll just pick the closest standard value that's put in here, and that's going to throw this off ever so slightly. And you do that a few times, you'll have an amp that works, that sounds good. The average person will love it, but it's not perfect. And what he shot for here was perfect. So I like that. So I'm going to try it. I've never tried this design. It's something new and exciting, so that's the one I'm going to try. I wanted a volume control on mine so that I can basically crank my MP3 player all the way up and not worry about setting the volume from there. I can use this volume control. And I thought I'd do something a little different, and that is I just built this little filter circuit, and I'm using a tapped volume control. So this volume control at about, I think it's about 70%. There's a fourth wire. And you'll see this on a lot of amplifiers. I mean, even like the Pioneers that I did the restorations on, those all had loudness switches, and believe it or not, they all use this pot. So it's not just tube, but solid state as well. Basically what you're doing is you're tapping off part of the signal, of your input signal, and then you're partially adding a type of tone filter to it, okay, which is going to kind of shape, depending on the values of these three components, you're controlling the ratio of bass to treble. So it's kind of like having a preset bass and treble control that attenuates itself, because as the wiper goes past that tap, this is going to have more or less influence. So at the lower volume levels, this will have a lot more influence. As you get to the higher volume levels, this is going to have less of an influence as you go past it. So it's a neat little simple design with three components and a switch. So I'm going to try that, and we're going to experiment with these values till we find one that works for us. I did add a capacitive coupling in here. That gives me more latitude to do these things on this end. Okay, again, I'm going to see how this works. For voltage regulation, I basically am using a transistor. I'm going to use a solid state voltage regulator. This is not just your normal transistor. This is a transistor that you use in a horizontal output circuit of high voltage for a television. Okay, so this is a TV horizontal output transistor. They're rated about 150, 200 watts. I'll be right back. Okay, but more important, they're rated at very high voltage. This thing is good for up to 1500 volts. Okay, from collector to emitter. So it's designed for a high voltage circuit, okay? Because that's, you know, this is what's going to drive the flyback transformer that drives the picture tube in a color television. So that's a lot of power it dissipates. So it's perfect for the job. And all I'm doing is just a basic linear voltage regulator circuit, okay? So what you're going to do is your input's going to be your collector, your output's going to be your emitter. Your base voltage is going to be set based upon a couple of factors. Number one, you're going to take the voltage you want out of here minus plus your 0.7 volts is what the output's going to be, okay? So, or minus, I should say. So if I want this to be 285 volts, this needs to be close to 286 volts, okay? So if you notice, now I could use a resistor divider network here. And as long as this 320 stays a solid 320, that would work perfectly, okay? I just use a voltage divider. However, we don't know if this can fluctuate because of your, I mean, if your input voltage from your incoming line fluctuates, this is going to go with it. And since this is a step up, 1 volt of change here could be 2 or 3 volts of change here, okay? Which, when you rectify it, it could be even more. So this can go off. So I'm using a stacked set of Zener diodes. And if you notice, I'm using 100, yes, they make these too, 150 volt, 100 volt, and a 36 volt. And the current through this is you're going to take your maximum current coming out of your 285 volts, so however many MA that's going to be of current. You're going to use the gain formula, okay? So this one had a gain factor, average gain of 15, I believe it was. Okay, so you're going to take it, you're going to set this resistor here, this resistance is going to be determined by, I know I want 180 or 285 volts here. Okay, I know that I have 320 on average going in there. So if I take my 320 minus 285, okay, that's going to give me what? Shame on me. I should be able to do that in my head. My son can. 320 minus 285 is 35 volts, right? So we're going to have a 35 volt drop across this resistor, okay? Whatever resistor I put in here is going to be a 35 volt drop. So that in mind, I want this resistor to be the proper resistance to allow the amount of current, when you times that current by the gain for this circuit, it will equal the maximum current draw that I could have out here, plus a little fudge factor. Okay, which in this case, when I did it, it came out to about 5.6 K, gave me a good current rating. I actually needed somewhere around 8 MA, it says. Okay, is what I came up with. I needed about 8 MA. And then 8 times your 15, your gain factor. So anyway, it came out to 5.6 K. Was a standard value that I could use at 1 watt, which this circuit is not going to draw 1 watt, okay? Or at least this portion of it is not, okay? And I'm using 5 watt Zener diodes. The total circuit combined, all components are only going to draw about 2.28 watts. So, you know, the highest wattage is going to be the drop across this 150 volt, which is still not even going to be, you know, it's going to be a little less than half of that. So it's about 1 watt will be on this one. This will be less than a watt. This will be less than that one. And this will be what's left on this resistor. So all of these components should run cool, and they're well under their operating voltage or characteristics. With that in mind, then you don't really need a whole lot of capacitance on this end. So I'm only going with a 10 microfarad capacitor at 450 volts. Okay. And my heavy capacitance is going to be right here on the other side of my choke. And I'm going 250 microfarad at 500 volt. And the only reason I can do that, normally a tube like this, it would cause this tube to arc over with that much. But this choke is going to limit the current flow through the circuit to 200 mA. Okay, so basically what we're going to do is we're going to charge this cap up slowly, so the inrush current doesn't damage the tube. And then this is going to act kind of like a surge suppressor, okay, or a surge taker. So if I hit a heavy bass note or something with my amplifier, with my output section, and I draw in excess of 200 milliamps for a short duration, this capacitor will start to take up that power. Okay, so it's a very simple power supply. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 components. 9 components, and that's a regulated power supply with the 2 voltages that I need to feed my amplifier. And it's very well regulated. So that's it. That's what we have. And I'm going to end this part 2 here. I'm still a couple weeks off of receiving the output transformers, but I now have everything collected up that I want for the amplifier except for the 2 output transformers. So our next step, part 3, we're actually going to start drawing the layout of the amplifier. Alright, the physical layout. So I hope you enjoyed this. I hope I didn't bore you to death. I hope some of this was interesting. I know there will be people who will comment out there that they this, that, or the other thing, and I welcome that. We're all going to learn together, and that's what I like the best about YouTube. That's why I do this. We can all learn things together. There's people, I'm sure, that know way more than I do about this. This is a hobby for me. I work with tubes that work off of 150,000 volts at 1 amp and produce radiation. They don't produce sound. And that's where my field of expertise is. This is my hobby. This is what I do because I like it. And it's fun. So I'm learning every day. That's why I do this. And for those of you who are learning and who have a hobby in this and enjoy it, I hope you enjoy this video. And again, any comments are welcomed because that's how we all learn, is from comments. So, from interacting with one another. So if you liked it, give me a thumbs up. And part 3 will be coming as soon as I get a chance. My work week is going to get really busy the rest of this week, so I don't know when I'll get the next video out, but we'll see. So until then, so long and have a great week.